All right, welcome back. We're looking at Math 1910 here, Chapter 2, Section 6. This is the end of Chapter 2 for us as well. All right, but we're going to be getting into related rates. Okay, so, we're actually going to be applying these derivative rules that we have to some real-life scenarios and, kind of see how they relate to, a lot of real-life problems. All right, so we've, had to use the chain rule a lot so that we can find something implicitly. All right, we're going to use the chain rule to find other related rates as well, because we're going to start doing things in terms of different variables, all right, volumes, heights, time, all these different variables. So we can see that, differentiating something implicitly can really help us out when we get to, these kind of scenarios here. All right, so, we want to talk about rates. So our first example, we're talking about a conical tank, and we want to be able to find the volume, all right, or the radius or the height, or the rate at which it's filling, whether it's the volume filling, or the rate at which the radius is expanding, or the rate at which the the height is growing. Okay, all very important things, so that if we need to time something out or do all these great calculations with it. Okay, so this is one where you're actually going to need to know all your area and volume formulas to get through this one. So bringing back some geometry skills. All right, so this is for the volume of a cone. Okay, remember the volume of a cone is 1/3 pi r squared h. Okay, so we can rewrite it here as pi over 3 r squared h, but it's really pi r squared h, and it's 1/3 of it when we do that. So like essentially, the volume of a cylinder is pi r squared h. Okay, but remember, a cone is 1/3 of a cylinder, so that's how we can relate those. So if you know a cylinder, you know a cone, essentially. So we can work through this. So when we want to take the related rate here, we can find it depends on which variable we want to take the related rate with. So if this scenario works out, okay, we're going to do everything with respect to time. So we're going to take the derivative of volume with respect to time, and we're going to take the derivative with r with respect to time, and with h, so with the radius and the height with respect to time. So when we do that, okay, we write it as d dt of v equals d dt of 1/3 pi r squared h. So when we do that, all right, we know that the derivative of volume with respect to time is just going to be dv dt, all right, because it's just volume, it's the derivative of v, which is 1 dv dt. All right, the pi over 3, that's a constant. We bring that out, okay? So then we have to take, with respect to r, with respect to h. What you need to know, and why it looks backward, is that's a product rule. R squared times h is a product rule. So it's first times the derivative of the second, plus the second times the derivative of the first. So that's a product rule there. So we're going to take r squared times the derivative of h, which is dh dt, plus h times the derivative of r squared, which is 2r dr dt. Okay, so we have everything as dv dt, dh dt, and dr dt. Those are all rates. Okay, the rate of volume with respect to time, the rate of height with respect to time, and the rate of the radius growth with respect to time. So we can rewrite this equation here as the rate of volume growth is pi over 3 times r squared dh dt plus 2rh dr dt. Okay, so that's just rewriting it. So we can find the rate of change for any one of those. Now, when you get problems in your homework, it's going to tell you like how fast the height's growing and calculate the volume, or how fast the radius is growing, and that sort of thing when we work through these. Okay, so let's do an example here. We have two rates that are related. All right, so suppose x and y are both differentiable functions of time, t, and are related by this equation, y equals x squared plus 3. So we want to find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. So we've received some very important information here. We know the rate of dx dt, okay, it's 2. But we don't know the rate of dy dt, that's what we're looking for, and we're given an initial condition here of when x equals 1. All right, so let's go ahead and get started here. So we want to, implicitly differentiate the y equals x squared plus 3. All right, so we're going to use the chain rule, and we're going to take everything with respect to time. So dx dt, okay, the bottom variable is the one that we're always taking the derivative with respect to. Okay, so we're going to start with the original equation, y equals x squared plus 3, and take the derivative of y with respect to t and the derivative of x squared plus 3 with respect to t. Alright, so the derivative of y with respect to t is just dy dt. The derivative of x squared is 2x dx dt, and the derivative of 3 is 0. Alright, so we're using the chain rule there. So we're left with dy dt equals 2x dx dt. Now we have some initial conditions. Alright, we have our rate. We know that we're given dx dt is 2, and we're given x equals 1. So we substitute in the value of x equal 1 and dx dt equals 2. Alright, and do our calculations. We get 2 times 1 times 2 is 4. So dy dt, the rate of y with respect to time, how fast y is changing with respect to time, is 4. Okay, so it's basically breaking it down. We take the original equation, we differentiate it explicitly, and then, implicitly, and then we substitute in the given values that we know. Now, I mean, technically that one's kind of explicitly because we already had it in y equals form, but since we're doing it with respect to a different variable, all right, we got to be careful with that. Okay, so we're going to do a mathematical model for the most part from the next few examples where, we're going to have to interpret a paragraph and solve some different things. Okay, remember the live stream is going to include more examples when we do this. Okay, and I'll get into more detail as well. All right, so let's talk about ripples in a pond. Very common related rate problem here. We have a pebble that's dropped into a calm pond. It's causing ripples in the form of concentric circles. Remember, concentric circles are circles inside of circles inside of circles inside of circles. So, imagine yourself throwing a pebble out into the pond and you can watch the circles ripple towards the shore. All right, but the circles are concentric. Okay, the radius r of the outer ripple is increasing at a rate of 1 foot per second. In my mind, I'm already thinking that's dr dt because it's giving me a rate. Okay, and that rate is related to r. So that tells me dr dt is 1 when I read through this. All right, then it says when the radius is 4 feet, so that's r equals 4. At what rate is the total area? That's telling me a rate of total A. That's telling me dA dt of the disturbed water changing. So I'm given dr dt, I'm given r, and I need to find dA dt. And what are we making? We are making circles, and we know the area of the circle is pi r squared. So that's the equation that we're going to have to differentiate, is pi r squared. So we know that area is pi r squared, and when we differentiate that, remember pi is a constant. All right, and then the approach for this is to write down what you have. So as I was reading through that, I told you, mentally I'm pulling out dr dt, I'm pulling out r, so I know all those, and I write those on the side. I need to involve the equation a equals pi r squared, right? Area is pi r squared because we're talking about a circle, so that's why I'm using that equation. I'm given dr dt, I need to find dA dt when the radius is 4. So all that information is what's pulled out of the paragraph. So that's an approach you should take when you're doing your problems, is be able to pull out that information and write out what each specific part is as you go through. All right, so now we have to differentiate with respect to t. So dA dt, all right, so the derivative of a with respect to time and the derivative of pi r squared with respect to time. Remember, pi is a constant, so we're going to factor that pi out in front here. So the derivative of a with respect to time is dA dt, and then the derivative of r squared is 2r dr dt. So we're going to have pi times 2, or 2 pi r dr dt is equal to dA dt when we do that. Okay, so just a chain rule there. Now we substitute in the values we have. We have r, it was given to us as 4, and we were given dr dt is 1, and asked to find the rate of change of the area. So we're able to substitute in the values that were given to us. All right, so we got 2 times pi times 4 times 1, and our answer is 8 pi square feet per second. We know it's square feet per second because area is in square feet. All right, and time was given to us in seconds. Okay, so hopefully this is starting to click a little bit. These aren't too bad. So what this really means, when the radius is 4 feet, all right, the area is changing at a rate of 8 pi feet per second, all right? All right, so this one, I'm not going to talk about too much with this one. This one I want you to write down These are just, kind of steps or guided steps for solving the problem, okay? So the first one, we identified all of the given material that's in the paragraph. We write the equation, or we pick out the generally associated equation for that. We differentiate both sides with respect to time. All right, and then substitute based on values we have. All right, so let's take a look here at some different mathematical models. All right, and how to relate those to the words. Okay, the velocity of a car after traveling for 1 hour is 50 miles per hour. So we know distance, right? Okay, over time, that's our velocity. So that's our 50 miles an hour. And we know time is 1 because it's 1 hour. Okay, so that's what we're really looking at when we do this. All right, water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Cubic meters tells us it's a volume. All right, so that's our dV dt. That's the volume that it's being filled in. Okay, 10 cubic meters per hour. Okay, and then it depends on the size, what shape the pool is. All right, if it's a circle versus something that's rectangular, that would change the equation for that one. Okay, we have a gear is revolving at a rate of 25 RPMs, and we have to know that 1 revolution is 2 pi radians. So theta, okay, is our angle of revolution because we're going in a circular motion, right? It's rotating. So we know that d theta dt, all right, is 25 times 2 pi radians per minute. Okay? If we talk about population versus time, right, we have bacteria increasing at a rate of 2,000 per hour. So x has to represent our population, and dx dt, the rate at which we're growing, is 2,000 bacteria per hour. Okay, so just how we, pull those things out. This is probably one of the most common related rates. It's usually, tanks and ladders sliding down the wall, because we got to relate, specific geometric equations or things like that for us. So a ladder that's 10 feet long rests against a vertical wall. So it's important that we understand the ladder and how it's leaning against a wall. So we're going to create what shape with a ladder leaning against a wall? We're going to create a triangle. So you need to know that since the ladder's rate, the ladder itself, physically, all right, is 10 feet long. So that's our hypotenuse, because how it's leaning against the wall. That's the hypotenuse of the triangle, okay? If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, okay? Well, if we were to graph that and draw the triangle, that would be x, right? So that's dx dt. It's sliding away from the wall. Okay, that's the horizontal piece. So that's dx dt. We want to find how fast the top of the ladder is sliding down the wall. That's telling me dy dt. We're going down. And y is how fast it's going up and down the wall. You do have to keep track of negatives for that. And we want to find how fast it's going when the ladder is 6 feet from the wall. That's when x equals 6. That's our distance from the wall. Okay? So we are given dx dt. We are given x. Okay? We're given z. Alright, we are. It's 10 feet. It's the ladder. And then we're going to have to find y and dy dt. We need y to find dy dt because we have to have our equation here. So you got to start thinking about what equation here are we going to talk about that involves a triangle. All right, we have a vertical component, a horizontal component, and a hypotenuse. All right, so I'm hoping you're thinking, right, this ladder, makes a 90-degree triangle. So you should be thinking Pythagorean when it comes to this. Okay, so if we sketch it out, it makes more sense. Okay, we have x, and it's sliding away from the wall. So that's dx dt. Sliding down the wall is dy dt. All right, and we know the ladder's length is not changing. The ladder will always be 10 feet in this scenario. All right, so we got to make sure that we set everything up correctly. So always sketch a picture for yourself when it gets to related rates, okay? We know we're using a triangle, and we've identified what dx dt is, and we label it, and we've identified what dy dt is, and x and y, and the hypotenuse, all right? Now we're ready to roll on this problem here. So it's a Pythagorean theorem. X squared plus y squared equals, or c squared, or the hypotenuse squared, right? Or a squared plus b squared equals c squared, however you want to see it. But we're going to go in terms of x and y. all right, just for horizontal and vertical components. So we know how to come up with this, all right? That's just Pythagorean, okay, theorem. When we do this. So when we do this, all right, now we have to do what? Implicit differentiation. But before that, we need to find out what y is. We know what x is, okay, because we need to find it at 6. So we have to know the specific value of y. And we are going to do our implicit differentiation on this. So this is kind of a multi-step related rate problem when we work through this one. All right, so if we implicitly differentiate this, all right, the derivative of x squared is 2x dx dt. The derivative of y squared is 2y dy dt. So we have 2x dx dt plus 2y dy dt, and the derivative of 100 is 0, right? It's the derivative of a constant. So we solve this for dy dt because that's what we're looking for, and good, it works out negative. It better be negative because the ladder's going down. So make sure we know that negative is involving the direction. So dy dt equals negative x over y dx dt. So we just solved that, all right, for dy dt. Then we have to substitute what is given, all right? And as I said before, we had to find y using the Pythagorean theorem, okay? So you know that x is 6, right? So 6 squared is 36, 100 minus 36 is 64, square root of 64 is 8. So that's where the 8 came from using the Pythagorean theorem. And we know the rate was 1 foot per second as it was going away. So we plug in 6 for x, 8 for y, 1 for dx dt, and we get, as we simplify it down, negative 6/8 feet per second, which reduces to negative 3/4 feet per second. So that means the ladder is sliding down the wall at 3/4 of a feet, or 3/4 of a feet, that's incorrect English, 3/4 of a foot per second, okay? Let's do another one here. We got a water tank. It's in shape of an inverted circular cone. What does that mean, right? So just essentially, you know, a cone. We have a radius that's 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, that tells me it's a volume, right? Okay, find the rate at which the water level is rising. So water level is height. So I need to be looking for dh dt, all right, when height is 3. All right, so there's a lot of factors that kind of play into what's going on here. So, you know, we know dv dt is 2 meters cubed per minute. We know the height is 3, and we have to find dh dt when we do this. Now, we don't have dr dt, so we're going to have to find something that relates h and r to kind of simplify this problem down. Okay, so what we need to do is come up with a nice ratio. So if we draw this out, we can see the actual water tank itself, okay, has a radius of 2 and a height of 4. Now for us, we have to know that we want to find when height is 3. So we have to come up with an equation that relates these two, because our height's changing as we're filling it with water. So we've got to change the, the set parameters of the cone to our rate parameters as we go through. So we should know, all right, from the first part of this lecture, volume of a cone is 1/3 pi r squared h. Okay, we have to relate r and h, and this is because we don't have dr dt. So if you're not given, if you have 3 different rates to a problem, and you're not given 2 of them, and one of them you have to find, what you need to do before you do the differentiation is find an equation that relates the 2 variables, so that you can rewrite the entire equation all in terms of one variable that you have the rate for when you do that. So for us, it's r over h is related to 2 over 4. Okay, that helps us understand that r is h over 2. That's important because we're going to take that h over 2 and we're going to replace it into the r squared. That way our volume equation is all in terms of h. Okay, because we're looking for dh dt. We have no dr dt, so we have to do it all in one variable that we know. So before we take the derivative, we replace r with h over 2. So it becomes h over 2 squared. So we simplify that down before we take the derivative. So our volume equation turns into pi over 12 h cubed. Y over 12. Well, we have to square that. So that becomes h squared over 4 times h. So that's where the h cubed comes from. And since it's h squared over 4, 4 times 3 is 12. Now we can take the derivative. So we're going to find dv dt. Alright, so when we do that, it becomes 3 pi 12, or sorry, I can't speak today, 3 pi divided by 12 times the derivative of h is h squared dh dt. It's 3h squared dh dt. We've already talked about that 3 being down in front. Now we can substitute in. We know h is 3, and we know dh dt is 2. So we substitute in all of our given values, okay? What we have, you have to solve it for dh dt in the long term, okay? You can substitute in the values you want and then solve. Right here I've solved it first for dh dt, then substitute in my values, whatever you want to make sure that it works out, okay? But when we substitute everything in, you should get 0.28. So what I suggest, working through these videos is, on a separate sheet of paper, go back to the beginning and see if you can rework through these, on your own without me guiding you through it and doing that sort of thing. We're going to do one more example here, but I would rework these problems a couple times just so that you kind of get in the habit of understanding, what's going on. All right, our last example here. We have a man walks along a straight path at a speed of 4 feet per second. Okay, we have a searchlight. It's located on the ground 20 feet from the path, and it's keeping focused on the man walking. Okay, at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so we're going to be changing theta here. So we can see that what kind of triangle is that? That's a right triangle, and our theta is going to be changing. So we're going to be looking for d theta dt. So we've got to find something that relates that x. Okay, the x is the direction the man's walking, so we need to know dx dt, right? And then we know that the spotlight is 20 feet from him when he was directly across from it, so that's going to stay fixed. That's our y. So we have to be able to relate this, okay? So we got to understand what's d theta dt, dx dt. Do we need dy dt? Do we need any of these other things? So let's talk about relating it. All right, so we know dx dt is 4 feet per second. Okay, that's how fast the man's walking. And we want to find out when he's gone 15 feet from the start point. All right, so we know that x is 15, and we want to find d theta dt. So for us, the easiest equation is using trig. All right, tangent is opposite over adjacent, so it's going to be x over y, all right, equals tangent of theta. That helps because that gives us a form of theta for us to use d theta dt. Okay, so if we solve this for x, okay, x equals 20 tangent of theta. Why do we want to do that? So we can differentiate with respect to time. All right, so that way we don't have to worry about fractions and quotient rules and things like that. So when we do that, the derivative of x is dx dt. The derivative of tangent is secant squared theta. All right, and then d theta dt. So that's our full derivative there. All right, so hopefully we're good. Now we have to be able to relate and find theta. All right, we know theta because we're talking about when x is 15. All right, so we can substitute x as 15 over 20. All right, and you can be able to do like tangent inverse to get that, okay? So we can also solve that. We're solving for d theta dt because we don't know that, right? So in order to do that, we take dx dt, divide it by 20 secant squared theta. And remember, we can rewrite secant in terms of cosine so that it's in the numerator. That's all we've done there. We've divided both sides by 20 secant squared theta and rewrote secant in terms of cosine, all right, so that it can be in the numerator, all right, because our calculator also uses that as well, okay? So if we know that x is 15, the length of the beam is 25, we can conclude, if we want to use cosine of theta now, because that's what we don't need the tangent. We could have used tangent and worked through a little earlier. But if we know cosine now of theta is 4/5, okay, we can do cosine inverse of 4/5, all right, and that'll tell us what theta is when we do that, okay? So we don't need to do that though, because we can sit there and substitute in the value of cosine based on our trig ratio. So we can say that d theta dt is 1/5 times 4/5 squared. So we get 16 over 125, which is 0.128 radians. Okay, so there's a couple different ways we can, work through that and do that calculation. So, one's just using the ratio like we learned last semester. All right. So, like I said, take these problems and, rework them a few times so that you truly understand, what's going on and how to work through them. All right, I think I said earlier we're going to do one example. We're going to actually do one more example here. We're going to do this one. We have example 6. We have air is being pumped into a spherical balloon so that the volume is increasing at a rate of 100 cubic centimeters per second. So that tells me that's dV dt. How fast is the radius of the balloon increasing? So I need to find dr dt. And it tells me the diameter is 50 centimeters. So I might need to use diameter. I might need to use radius. Just kind of depends. We need to know the volume of a sphere. Okay, that's 4/3 pi r cubed. Okay, so that's our volume of a sphere that we have to use. And I believe I attached all the trig formula sheets and things like that, or in the volume formulas and area formulas and that sort of thing for you guys. If you don't have one of those yet, let me know. We'll get them, or they're on the inside cover of your book as well. Okay, so just to recap, we're given dV dt. All right, is 100 centimeters cubed per second. Diameter is 50, so that means our radius is 25. And we want it in terms of radius because we're looking for dr dt when we do this problem. So we know the volume of a sphere is 4/3 pi r cubed. All right. Now, do we have everything we need? We have, this is only in terms of two variables, so it's not as bad, right? There's nothing else that we really need to find. We have r. We're going to look for dr dt, and we have dV dt. So there's nothing else relating any variables that we have to do. This one's pretty straightforward. We just take the derivative of both sides. So the derivative of v is dV dt. All right, and the 4/3 pi, that's a constant. So we just take the derivative of r cubed, which is 3r squared dr dt. So that 3 times 4 becomes 12 on top. And then 12 divided by 3 is 4. Okay. Then we need to solve for dr dt. So we're going to take dV dt and divide it by 4 pi r squared. Okay, so that's how everything kind of gets on the bottom there. So once we do that, we substitute in our given values. Okay, we know what dV dt is, and we know what r is. So we substitute in our given values, and we find that dr dt is 1/25 pi. Alright guys, that's the end of this lecture. So hopefully you understand related rates now. The whole point is pulling out the specific information that you're given in the problem. All the rates that you're given and all the constants that you're getting. Whether you're doing something in terms of x and y, when we have some sort of triangle, or we have a rectangle and we have x and y, or we have a sphere, right? We have a cone, we have a cylinder, all these different things. So we've got to relate the geometric shape that we're doing and use the equation involved with that geometric shape and be able to take the derivative of it. Okay, and sometimes, like we did with the cone problem, we have to relate one variable in terms of another, because we just if we have 3 rates in the problem, we're only given one and we have to solve the other one. Okay, we have to find that rate or that other variable that relates everything for us to connect it together. So as usual guys, email me if you got any questions. Let me know if we need to team meet or Zoom meet. Please make sure that you focus in on the live lecture when I'm doing it as well, so that you can see the other examples that we're going to do, and I can work through these if you're a little rusty on a few of the algebra steps and things like that. So I know I skipped through a little bit of the algebra. I'm assuming that you know what you're doing there. We spent that first chapter reviewing algebra anyway. So alright guys, have a great day. See you in class.